A hurricane so violent its winds exceeded 500 miles per hour. Cloud towers punching through the atmosphere to the edge of space. Continental scale tornado swarms shredding landscapes thousands of miles from the storm's center. This isn't a disaster movie. It's the Hypercane, a theoretical megastorm so extreme it breaks the fundamental rules of planetary weather. The physics are sound, the evidence suggests they actually happened, and they may have killed the dinosaurs. Modern Category 5 hurricanes top out around 160 to 200 miles per hour, limited by the natural thermodynamics of Earth's current atmosphere. They're capped by the troposphere at about 10 miles altitude, flattening into the familiar disc shape visible from space. They're devastating, but they're constrained by physics. Hypercanes operated under different rules entirely. The concept emerged in the 1990s from atmospheric scientist Carrie Emanuel, who asked a deceptively simple question. What happens if we remove the normal thermal limits? What if the ocean becomes hot enough to fuel something beyond a hurricane, something that transforms atmospheric science from weather prediction into planetary catastrophe modeling? The answer was the Hypercane, not a bigger hurricane, a fundamentally different atmospheric phenomenon occupying the space between the weather system and extinction mechanism. The winds don't just blow faster. At 500 miles per hour, air stops behaving like a fluid and begins acting like a continent-sized cutting tool, moving fast enough to strip topsoil down to bedrock. The central pressure doesn't just drop lower, it creates a near vacuum column that pulls structures apart from the inside. The storm doesn't just grow larger, it achieves diameters exceeding 1,500 miles, dominating entire continental zones simultaneously. And the destruction doesn't end when the winds stop. The Hypercane punches through the stratosphere, injecting ocean water and chlorine directly into the ozone layer. It spawns swarms of tornadoes across thousands of miles. It fundamentally alters atmospheric chemistry, stripping away Earth's protective UV shield for decades after the storm dissipates. This is the story of what happens when Earth's physics are pushed to their theoretical limits. When ocean temperatures rise not to 85 degrees Fahrenheit, but to 120 degrees Fahrenheit. When atmospheric energy budgets explode beyond anything in the modern climate record, when a single storm system becomes powerful enough to trigger mass extinction. The Hypercane may sound impossible, but the mathematics are rigorous, the physics are established, and the geological record whispers that during Earth's most catastrophic moments, when asteroids struck deep oceans or volcanic supereruptions superheated entire sea basins, these monsters actually formed. Normal hurricanes need warm water. The threshold sits around 80 degrees Fahrenheit, warm enough to drive evaporation, fuel convection, and sustain the heat engine that powers tropical cyclones. Modern ocean temperatures in hurricane-prone regions rarely exceed 88 degrees Fahrenheit, even during peak season. That thermal ceiling limits what's possible. Category 5 represents the upper boundary of what Earth's current climate can produce. A Hypercane requires breaking that ceiling completely. The threshold temperature sits at approximately 120 degrees Fahrenheit, 50 degrees Celsius. Water hot enough to cause burns on contact. Temperatures that would kill most marine life outright. Heat that shouldn't naturally exist across millions of square miles of ocean surface. But shouldn't exist is different from can't exist. Under specific catastrophic conditions, ocean temperatures can spike far beyond normal limits. Two mechanisms stand out. Massive asteroid impacts striking deep water, and colossal underwater volcanic eruptions that inject heat directly into the sea. The Chicxulub asteroid impact 66 million years ago provides the most studied scenario. A mountain-sized rock 6 miles wide struck the Gulf of Mexico, traveling over 20 miles per second. The kinetic energy, equivalent to billions of nuclear weapons detonating simultaneously, converted instantly to thermal energy. The impact didn't just create a crater. It flash vaporized billions of gallons of seawater and superheated the surrounding ocean across a region spanning hundreds of miles. Impact ejecta, vaporized rock and water thrown into the upper atmosphere, fell back to Earth over the following hours and days, creating a thermal blanket that trapped heat. Greenhouse gases from vaporized limestone added to the effect. The ocean couldn't cool through normal evaporation and current circulation fast enough. heat accumulated. Regional ocean temperatures spiked to levels never recorded in human history. For weeks or months after impact, vast stretches of the Atlantic and Gulf of Mexico sat at temperatures approaching or exceeding the Hypercane threshold. The heat had nowhere to go. The thermal engine was armed. Underwater volcanic eruptions provide the second trigger mechanism. Large igneous provinces, massive volcanic events that flood regions with lava, sometimes erupt through ocean floors or shallow seas. The Siberian Traps eruption 252 million years ago, associated with Earth's worst mass extinction, released magma across millions of square miles. Portions of this eruption occurred underwater. When 2000 degrees Fahrenheit molten rock contacts seawater, the heat transfer is immediate and catastrophic. Unlike surface eruptions where heat radiates into atmosphere and space, submarine eruptions pump thermal energy directly into the ocean, with nowhere for it to dissipate quickly. A volcanic fissure miles long, continuously injecting magma into seawater over months or years, creates expanding zones of superheated ocean. The process becomes self-reinforcing. Hotter oceans evaporate faster, increasing atmospheric water vapor. Water vapor is a greenhouse gas. More greenhouse effect traps more heat. The ocean heats further. Evaporation increases, the cycle accelerates. Eventually, the ocean reaches a state fundamentally different from anything in modern climate. At 120 degrees Fahrenheit, seawater becomes a massive battery of stored thermal energy, desperate for release. The only mechanism capable of dissipating that much energy that quickly is catastrophic storm formation. Storms that tap the entire thermal reservoir and convert heat to kinetic energy on a planetary scale. Normal cooling mechanisms fail. Ocean currents can't mix hot surface water with cooler deep water fast enough. Atmospheric heat exchange becomes inadequate. The thermal anomaly persists, spreading across ocean basins, and somewhere in that superheated zone, atmospheric pressure drops. Convection begins, evaporation accelerates. A hypercane starts to form. The storm doesn't build gradually like normal hurricanes, organizing over days as they drift across tropical waters. With 120 degrees Fahrenheit fuel available, intensification happens rapidly. Within hours, wind speeds exceed any modern hurricane. Within a day, the system achieves superstorm status. Within days, it becomes something unprecedented, a hypercane in full fury, with physics operating at the theoretical maximum of what Earth's atmosphere can sustain. The ocean that birthed it begins to cool as the storm extracts thermal energy. But the damage is done. The hypercane is loose, and the planet will bear its scars for millennia. A modern Category 5 hurricane tops out around 160 to 200 miles per hour. Those winds can peel roofs off buildings, snap trees at the trunk, and turn debris into lethal projectiles. They represent the upper limit of what atmospheric physics can generate when ocean temperatures sit at 80 to 85 degrees Fahrenheit. Increase the ocean temperature to 120 degrees Fahrenheit, and the physics don't scale linearly. They explode. Hurricanes are heat engines. They convert thermal energy from warm ocean water into kinetic energy, wind. The greater the temperature difference between the ocean surface and the upper atmosphere, the more efficient the engine becomes. It's not speculation, it's thermodynamics. Kerry Emanuel's theoretical models calculated what happens when you feed that engine ocean temperatures 35 to 40 degrees hotter than normal. The central pressure drops into ranges never recorded in modern meteorology. Potentially below 700 millibars, normal sea level pressure sits at 1,013 millibars. A 300 millibar pressure drop creates a gradient so steep that wind doesn't just blow, it erupts. The result, sustained winds exceeding 500 miles per hour. At those speeds, air stops behaving like a fluid. It becomes a cutting tool. Modern sandblasting equipment uses compressed air at 100 to 200 miles per hour to etch metal and strip paint. Hypercane winds carry 6 to 25 times that energy. The force isn't linear. Doubling wind speed quadruples the force. Winds at 500 miles per hour carry roughly 10 times the destructive power of a Category 5 hurricane. Topsoil doesn't erode, it strips away down to bedrock across thousands of square miles. Vegetation doesn't break, it disintegrates into splinters, and those splinters become projectiles moving at aircraft speeds. Exposed rock faces don't weather. They get sandblasted smooth. The landscape doesn't just suffer damage, it undergoes geological resurfacing. Buildings, forests, soil Anything not anchored to bedrock disappears. The wind zone extends hundreds of miles from the storm center. The eye wall itself might span 100 to 200 miles in diameter, larger than entire modern hurricanes. The total storm system could reach 1,500 to 2,000 miles across, dominating entire continental zones simultaneously. A hypercane positioned over the Gulf of Mexico would generate maximum winds from Texas to the Carolinas simultaneously. The storm wouldn't threaten regions sequentially as it moved. It would attack them all at once. The pressure differential creates effects beyond wind. Inside the eye, pressure drops so low that structures experience explosive outward force from normal air pressure trapped inside buildings. The pressure gradient literally pulls buildings apart from within before the winds arrive. Water bodies within the eye region would experience abnormal drops in sea level as the vacuum effect lifts water into the atmosphere. The eye itself becomes a column of rapidly rising air extending miles upward, a chimney effect creating suction from below. This updraft contributes to the storm's catastrophic footprint, generating wind patterns that defy normal hurricane behavior. The size amplifies every effect. Modern large hurricanes span 300 to 500 miles in diameter. A hypercane at 1,500 miles doesn't just affect more area, it dominates atmospheric circulation across entire ocean basins. Multiple climate zones experience maximum conditions simultaneously. Coastal regions and continental interiors face the same fury at the same moment. The storm doesn't move quickly either. Modern hurricanes travel at 10 to 20 miles per hour. A hypercane, drawing energy from a vast region of superheated ocean, might stall or drift slowly across its fuel source. Days of sustained 500-mile-per-hour winds. Days of continental-scale sandblasting. Days where the atmosphere operates in a state of sustained violence unprecedented in modern weather. When the winds finally stop, when the thermal energy dissipates and the storm collapses, the affected region emerges transformed. Not damaged, erased, scraped down to geological substrate. Every meter of topsoil gone, every structure flattened, every ecosystem sterilized by mechanical force alone. But the wind is only the beginning. The hypercane's true catastrophic legacy unfolds in the sky above, where the storm has already begun rewriting atmospheric physics in ways that will outlast the winds by decades. A typical hurricane reaches upward until it hits the tropopause, the atmospheric ceiling, where the troposphere ends and the stratosphere begins, roughly 10 to 12 miles above sea level. At that boundary, rising air encounters a temperature inversion. The air above gets warmer, not cooler. Convection stops. The storm clouds flatten into the familiar anvil shape visible from space. The hypercane doesn't stop. The updrafts are too powerful. Air rising from a 120 degrees Fahrenheit ocean surface carries so much thermal energy that it punches straight through the temperature inversion. The convective tower keeps building. 15 miles, 20 miles, 25 miles. The storm cloud doesn't flatten. It penetrates deep into the stratosphere, a region where weather doesn't belong. At 20 miles altitude, the sky turns dark blue, then black. The air pressure drops to a few percent of sea level. The curve of the Earth becomes visible. This is the edge of space, and the hypercane reaches it. From the ground thousands of miles away, the cloud tower would appear as a white column rising beyond the horizon. The top would catch sunlight even after local sunset, glowing against the darkening sky. Lightning would flicker at multiple altitudes simultaneously, not just within the cloud, but between cloud layers separated by miles of vertical distance. From orbit, the storm would look alien. A massive white vortex covering an area the size of Greenland, but with a central tower punching upward like a mountain made of cloud. The eye, potentially 100 miles wide, would appear as a dark hole boring down through the atmosphere to the ocean surface. The shadow cast by the tower would fall across surrounding cloud decks, creating a darkness visible from space. But the visual spectacle masks the chemical catastrophe unfolding in the stratosphere. The stratosphere is normally dry, a few parts per million of water vapor. It's isolated from surface weather by the tropopause boundary. That isolation protects the ozone layer, which exists between 12 and 19 miles altitude. Ozone blocks 97 to 99% of the sun's harmful ultraviolet radiation. Life on Earth's surface exists because the ozone layer exists. The Hypercane injects millions of tons of water vapor directly into this protected zone. Every second, the updrafts act as a planetary elevator, lifting ocean moisture and salt aerosols into the stratosphere at rates that overwhelm any natural removal mechanism. Water vapor in the stratosphere increases hydrogen radicals. Those radicals attack ozone molecules, breaking them apart. The reaction is catalytic. One water molecule can destroy thousands of ozone molecules before being removed from the system. Ocean spray carries dissolved chlorine as salt. In the stratosphere, ultraviolet light breaks down salt particles, releasing chlorine atoms. Chlorine destroys ozone through a similar catalytic process. One chlorine atom can eliminate tens of thousands of ozone molecules. The Hypercane combines both mechanisms. Water vapor and chlorine, injected continuously for days or weeks, catalytically destroying the ozone layer above and downwind of the storm. The stratosphere normally experiences wind speeds of 100 to 200 miles per hour at jet stream altitudes. Material injected into the stratosphere doesn't stay localized. Within days, stratospheric winds carry the water vapor and chlorine thousands of miles from the injection point. Within weeks, the contamination spreads globally. A single Hypercane over the Pacific Ocean could damage the ozone layer above Antarctica within a month. The destruction isn't subtle. Above the storm track, ozone concentrations could drop by 50 to 70% within weeks of the injection. The hole would be hundreds of miles wide, drifting with stratospheric circulation patterns. Ultraviolet radiation reaching the surface below would increase by 500% or more, and the effects would persist. The stratosphere doesn't clean itself quickly. Injected water vapor and chlorine remain active for months to years. Ozone production, driven by natural photochemical reactions, takes years to decades to restore pre-storm concentrations. The Hypercane's cloud tower would eventually collapse. The winds would die, the ocean would cool, but the atmospheric damage would outlast the storm by decades. Survivors on the surface wouldn't see the ozone destruction happening. There would be no visual warning. But within days of the stratospheric injection, the sun would become an enemy. Radiation that once sustained life would begin killing it. The Hypercane's outer circulation bands extend hundreds of miles from the eye. Wind speeds decrease with distance from the center. But even 500 miles out, sustained winds exceed 100 miles per hour. The storm is so large that different altitudes experience wildly different wind speeds and directions simultaneously. Upper-level winds race at 300 miles per hour eastward. Mid-level winds spiral inward at 400 miles per hour. Surface winds drag across the continental crust at 200 miles per hour. That vertical wind shear creates tornadoes continuously. Modern supercell thunderstorms generate tornadoes from moderate shear, wind speed differences of 30 to 50 miles per hour between altitudes. A Hypercane creates shear zones with 200 mile per hour differentials extending across thousands of miles of storm periphery. Every square mile of that shear zone becomes a potential tornado genesis point. The result isn't a few tornadoes, it's swarms. Dozens form simultaneously along the outer bands. As one dissipates, two more spawn nearby. The atmospheric conditions that create tornadoes don't pulse on and off. They persist as long as the Hypercane exists. Days, weeks. The tornado production never stops. These aren't ordinary tornadoes. They're feeding from apparent circulation already moving at 500 miles per hour. Modern EF5 tornadoes, the strongest on the enhanced Fujita scale, generate winds up to 300 miles per hour. Hypercane-spawned tornadoes inherit energy from wind fields already exceeding that. Vortex wind speeds could reach 400 miles per hour or higher. They last longer too. Normal tornadoes persist for minutes, occasionally an hour. Their energy comes from local atmospheric instability that exhausts quickly. Hypercane tornadoes draw from the storm's massive energy reservoir. They could maintain intensity for hours, carving paths not 5 or 10 miles long, but 50 or 100. The damage paths widen. Modern violent tornadoes create swaths a quarter mile to a mile wide. These could exceed multiple miles. The friction zone, where 400 mile per hour rotation meets the ground, would pulverize everything within reach. And there would be hundreds of them. The stratosphere sits 12 to 30 miles above Earth's surface, separated from the weather below by the tropopause boundary. That isolation matters. The stratosphere is dry, stable, and chemically balanced. The ozone layer exists there because conditions allow it. low water vapor, specific temperature gradients, and protection from surface contamination. The Hypercane shatters that protection. Every second the storm operates, updrafts inject thousands of tons of ocean water vapor directly into the stratosphere. Salt aerosols follow, microscopic particles of dissolved chlorine lifted from ocean spray. The injection rate overwhelms every natural removal mechanism. Water vapor concentrations spike from parts per million to parts per hundred. The stratosphere, normally desert dry, becomes saturated. That moisture triggers ozone destruction immediately. Water vapor increases stratospheric hydrogen radicals, OH and HO2. These radicals attack ozone molecules, breaking the 3-oxygen bond that gives ozone its UV blocking properties. The Hypercane combines both mechanisms simultaneously across a region hundreds of miles wide. Water vapor and chlorine, injected for days or weeks without pause, catalytically stripping the ozone layer above the storm track. The depletion begins immediately but accelerates over time. Within days of injection, ozone concentrations above the Hypercane drop measurably. Within weeks, the loss reaches 50 to 70%. A hole opens in Earth's UV shield, not the small seasonal polar ozone holes discovered in the 1980s, but a massive wound spanning thousands of square miles over temperate or tropical latitudes where life concentrates. Stratospheric winds ensure the damage spreads. At altitudes above 60,000 feet, jet streams move at 100 to 200 miles per hour, circling the globe. Injected material doesn't remain stationary. Within days, contaminated air masses drift thousands of miles downwind. Within weeks, they circle entire hemispheres. A Hypercane in the Atlantic injects chlorine that reaches the Pacific. A Pacific Hypercane seeds ozone destruction above Antarctica. The depletion becomes global within a month. Regional concentrations vary, but every latitude experiences measurable ozone loss. The protective blanket doesn't develop small holes. It becomes threadbare across the entire planet, thinning everywhere simultaneously. Ultraviolet radiation penetrates where it never could before, and the chemistry doesn't reverse quickly. Chlorine remains active in the stratosphere for years. Water vapor persists for months. Natural ozone production, driven by solar UV splitting oxygen molecules, proceeds at normal rates, but those rates assume normal destruction rates. With catalytic destruction accelerated by orders of magnitude, production can't keep pace. Recovery takes decades. The Hypercane dissipates within weeks. The ocean cools, the winds stop, the updrafts cease. But the atmospheric damage continues expanding long after the storm dies. Chlorine injected during the storm's peak still destroys ozone years later. Water vapor still generates hydroxyl radicals. The stratosphere, contaminated with surface materials, slowly cleanses itself through processes that operate on geological timescales compared to the storm's brief violence. Life on the surface wouldn't understand what happened. The sky would look normal, the sun would rise and set as always, but the radiation penetrating from that sun would have fundamentally changed. The invisible shield that made terrestrial life possible would be compromised across the entire planet. Minutes of exposure would burn skin. Hours would kill surface vegetation. Days would trigger the collapse of ecosystems from the bottom up. And there would be no shelter except darkness, no escape except night. For decades, while the atmosphere slowly healed from wounds inflicted in mere weeks by a storm that treated the stratosphere not as a boundary, but as another victim. The Hypercane ends. The winds drop. The ocean cools, the cloud tower collapses back below the stratosphere. Survivors emerge from shelters into silence where there had been only roaring chaos for weeks. The storm is over, but sunlight has become lethal. UVB and UVC radiation, wavelengths normally absorbed by the ozone layer before reaching Earth's surface, now penetrate unimpeded through the damaged stratosphere. Radiation levels spike to multiples of normal background. What was once life-giving light now carries enough energy to break molecular bonds in DNA, proteins, and cellular membranes. Minutes of direct sun exposure cause burns. Hypercanes weren't just storms, they were extinction delivery systems, apocalyptic convergences of wind, water, and atmospheric chemistry that operated at the theoretical maximum of what planetary physics allows. The math is sound. The triggers existed, and geological evidence whispers they actually happened, finishing what asteroids and volcanoes started and reshaping life's entire trajectory in the process.